All right. No, no, I'm just saying in general. Don't. Yeah. I should try better. Should have just wash hands more often. But anyway, so we're gonna talk about transformations. Shifting, stretching, reflecting. We did that for a parabola. We're now gonna apply this for all these types of functions. Now you might remember on the first day, and I did this with your parents on back to school night, when I did my little presentation here. So back to school night, or actually first day of school. Here we go. Yeah, it's like my kids and other stuff. But remember, I like showed you like Star Wars characters, and then I showed you this, right? And so what's happening is that we're actually working these functions out. So we've worked with parabolas quite a bit in the last couple of classes, right? Lines, we know how lines work. We've done this already, right? 1/x. Move this around the graphic calculator. We done exponential, right? We saw that, talk about asymptotes. We haven't really messed around with square roots or trig or absolute value or cubic. Logarithmic, I don't want to get into that. That's not full spring. But we've done a few of these already. And we've talked about how these can move around. And that's what we're going to do today. We're going to move an exponential around. We're going to move a reciprocal function around. We're going to move the cubic square root. Absolute value. We're going to move all these functions around a little bit. So you see we have x cubed, square root x, exponential, absolute value, 1/x. These are all called parent functions because they're the most basic equations for these types of functions. Just so we label these so you guys know the names, because we got to be pretty formal about this. That's called cubic because it's being cubed. That's called square root for obvious reasons. That's exponential because x is in the exponent, right? Exponential. Can't write. That's absolute value because you have an absolute value symbol. What's absolute value do, guys? What's the purpose of absolute value? Always positive. Thank you, Samara. 100%. All time comes out as being positive. And 1/x is called the reciprocal function. We could also call it a rational function as well. So it has two different names. Okay, we're not going to do this on a large graph paper. We're just going to kind of do this as a class. And we're just going to just understand how each of these graphs look. And then we're going to transform. And the transformations are going to be all the same as they were for parabolas. H, K are going to be the same thing. A is going to be the same thing. And you're going to see how A, H, and K serve the same purpose for any kind of function. Ultimately, we'll do the same thing with parabolas, so not parabolas, with trig functions and logarithmic functions and other crazy stuff. Before I get too carried away, the last page is going to be kind of your best friend. Has a list of all the functions that need to be comfortable with and the transformations that go with it. And notice that you see H and K every single time. You see A on the outside. So it's not any different than what it was for problems. Like probably A exponential squared plus K. It looks kind of crazy, but they all serve the same purpose. H is horizontal shift, K is vertical shift, A is stretching or flipping over. In general terms, we sometimes write like this. A times f of x minus h plus k of f of x is what function you're dealing with, whether it's absolute value, parabola, cubic, hyperbola, square root, exponential. And again, if A is greater than 1, it's a stretch. A is less than 1, it's a absolute value. So I meant it's going to be a compression. And if A is negative, it reflects. But before we do all that stuff, let's talk about how each of these is supposed to look. So I'll kind of I'll do some mini graphs down here. Kind of do it like this in a way. Okay. So x cubed. Let's think about it. Is there any reason why we need to restrict the domain for x cubed? We can plug in anything we want if we want to cube it. So what if I plug in 0 per x? What if I plug in 0 for this? What's y going to be? What if I plug in 1? What do I get? Now 2. 2 times 2 times 2. 8. Perfect. Good. So it rises pretty quickly. And if I plug in negative numbers, what if I play -1? What if you do -1 times -1 times -1? Multiply 3 negatives. -1. What if I do -2, -2, -2? Good. So the graph looks like this. That's how that looks. Okay. What about square root of x? Is there a restriction for the domain for that one? Can I plug in whatever I want, or is there a certain limit? You can't do negatives, unfortunately, right? But you can start with 0 and go up. So if I plug in 0, I get 0. Plug in 1, I get 1. Plug in 4, I should get 2. Because we know what square roots do, right? It's like find, yeah, go ahead. You're trying to find two numbers that multiply to what's on the inside. So it's going to generally look like this. It rises, but kind of slowly. 2 to the x. We kind of know what to expect there. If I plug in 0, I should get 1. What if I plug in 1 or 2? What do I get? Yeah, and it keeps rising. And it rises pretty quickly. But if I plug in negative numbers, does it ever become negative? It flips, right? Yeah, like 1/2 or 1/4. So we're reinforcing a lot of old stuff. So it looks like that. Absolute value. It's more. So it's always gonna be positive, right? It's never gonna be negative. It's always gonna be a positive number. So if I plug in like 0, 1, and 2, I get 0, 1, and 2. What if I plug in -1 and -2? 1 and 2 again. So they're mirror images of each other along the y-axis. In fact, actually, they're like two lines. One with a positive slope, one with a negative slope. That's actually what it truly is. It's a V. It's like a V shape. And lastly, 1 over x. We've kind of talked about this already. So we can't. What? There's one restriction. What's the one number I can't plug in for x? That's not okay. Yeah, I can't do 0. But if I could plug in 1 or 2, I get 1 and 1/2. Or if I plug in 4, it just gets to be a tinier fraction, right? If I plug in negative numbers, can I get the same thing, right? But they're negative numbers. So you get something like this here. So you have these guardrails, right? Like you have these things that we call asymptotes. Geez. And you have it for this as well. You don't have it for the other ones. That's because they don't, because the way the ranges and domains are set up. But you have for exponential and reciprocal functions. You have asymptotes. Plus, if you were to plug in like a small fraction, like what if I were to plug in like, I don't know, 1/10, and I flip it, I get 10. Or 1 over hundreds, I get 100. So it just keeps rising, So anyway, domain range. Domain range, domain range, domain range, domain range, domain range. Okay. So we're trying to understand how each of these are behaving before we start doing transformations with them. Tell me the domain for x cubed. What would you say the domain is? Anything, exactly. So usually I do an R with a line through the middle of it to say all real numbers. You can say all real numbers. You could also do this. Negative infinity. I'm not gonna have space for that. But you could do like this. That works. Or you do interval notation. I'm gonna lay off interval notation for now, but I am gonna kind of force you guys to start using it later in the year. It's more good. Totally 100%, yes, 100%. Again, yeah. But just in the interest of space, I'll just do that. Where else is my domain all real numbers? What other functions would the domain be all real numbers? Which one? 2x, it's the middle one. And where else? There's one more. As you look at the graph and think about the equations. Which other one has a domain of all real number? Like anything could work for x. Thank you, Lincoln. Perfect. Yes. Okay. Now let's talk about the range. The range seems to be pretty unique for each of these. For x cubed, it's all real. Anything has come out for y. Oh, well, I forgot to do the domain for root x. That's gonna be this. And that's gonna be all real except 0. You can't do 0 for 1 over x. Okay, domain. Sorry, range. So range is x greater than equal to 0 for. Sorry, the range is all real for x cubed. What's the range for root x? What's the lowest y value there? Yeah, and it's included and goes up. But see how this one's just y is greater than 0? Because 0 is not included. How about the range for absolute of x? What would that be? Yeah, just like the second one. Yeah, y is greater than equal to 0. And this one's all real except 0. Okay. These domain ranges will change when you transform. So look at number 4. We're asking to write a new equation for this transformation, to draw it, and give me the domain range of the transform graph. Before I do number 4, because it's going to get a little crazy, because a lot we're going to have to write, let's understand what these transformations are doing. But before I even do that, any questions on 1 and 2? All's good? Okay. Perfect. So again, you're trying to get more intimate knowledge with these functions. What is x cubed doing? What is root x doing? What is 2tx doing? What is absolute x doing? So we're good. The asymptote for oh, right here. Yeah. So that's gonna be all real except 0, all real except just the asymptotes impact into the domain range. So things that see how like we're not crossing the x-axis here. So we exclude that from the range. Notice that we're not crossing the y-axis. So we exclude that from the domain. So they are tied closely together. Actually, they're the same thing. And once we transform, you're going to see that connection even better. So, okay, let's keep moving. So let me clear the screen because it's getting a little busy. Okay, what does this transformation do? So this is going to be a stretch. I'm going to label as a vertical stretch. That's going to be up 4. And that's going to be right 3. So up 4 because you're adding 4, right? That should be intuitive both ways. -4, down 4. The x is different though. It's a bit counterintuitive. The x -3, don't go left 3. You go right 3 because your new x-intercept would be 3. Because 3 minus 3 is 0. And that'd be a new x-intercept. So you gotta be somewhat counterintuitive with the horizontal movements. This is a stretch, so it just gets, so it means you multiply y by 2. That's what happens there. Okay, now you have to write a new equation for each of these functions using this transformation. So let's do x cubed. How's that going to look? It's going to look like this. 2x minus 3 cubed plus 4. That's all. And set it equal to y, obviously. That's it. That's all you do.
That cubed or squared?
Ooh, thank you. Yes, it's cube. My apologies. And let me put the y next to the left. I don't know why I put it to the right. That's kind of weird. Okay, so we have the x cubed function. We're going to write it like that. Okay, let's do it for the square function. That's all. For the, what was the third one? It was 2tx, right? You're gonna write like this. Y equals 2 times 2 to the x minus 3 plus 4. Perhaps I have x, you're gonna write like this. So it's incredibly consistent. I'm putting 2 on the outside, minus 3 on the inside, plus 4 on the outside. And lastly, for absolute value, there's no exponents for absolute value. And then 1 over x, it's going to look like this. Y equals 2 up top, x minus 3 plus 4. Oh, geez, that is so hard to read. Let me switch colors. My apologies. Let's try maybe that color. Let's try red. Okay, let's do it down here. Okay, all's good. Okay. What's the domain range for each of these? Okay. Well, that's gonna get a little messy. We should talk about it. So let me I didn't give you guys enough space, did I? No, I'm sorry about that. Well, I'll kind of point to it over here. Our new domain range for each of these. I'm not gonna do the drawing of the graphs because there's clearly not enough space for it. But we can always, check it out in Desmos. You guys can do practice eventually, so I'm not too worried about it right now. For cubic, it doesn't matter. It's still gonna be all real anyway. That won't matter. But for square root, it will matter. Because how's that move? It moved 3 right and 4 up, right? So that endpoint, where was that endpoint originally for square root of x on your graph? Where was that originally? At what coordinates? The first point for square root of x.
0.
0, 0. We went 3 right and 4 up. So where's the new endpoint now? 3, 4. So your domain is going to be x is bigger than or equal to 3. And your range is going to be y is bigger than or equal to 4. Unless if you flipped it, then you have to make it less than or equal to 4. Exponential, still all real for the domain. And likewise for absolute value, still all real. That doesn't matter. But let's look at the range for exponential. They went 4 up, right? Where was the horizontal asymptote for the original C to the x graph? It was at the x-axis, right? Didn't we go 4 up? So what's the new horizontal asymptote now? So it's going to be y is greater than 4. So we're using a lot of good intuition. It's great. Okay, think about the absolute value. The vertex is at 0, 0, right? The sharp corner. You went 3 right and 4 up. Domain's still all real, but what's in your range for this? We're going 4 up. 4. Exactly. Good. 4. Y is greater than or equal to 4. And it includes 4. And lastly, for this one, what's going to happen is that we shifted 3 right. So it's all real except 3. Because you can't plug in 3 into the bottom. And the range is all real except 4. That's because Y can't be 4. Because what we've done now is we've shifted the output as well, right? So I feel you guys are gonna get much better with this because now we've seen this a few times already in two previous units. So you feel like, yeah, 3 right, 4 up. So that's how domain range are impacted. Okay, that was pretty thorough. I'm not going to do the graphs of these because just not enough space, but I trust you guys can put this in Desmos and figure it out. It's not hard to do. Questions? Good. Okay, let's keep moving. And just looking at time. Okay. Time's going fast. Okay. Well, I don't know if we'll get through all these notes today. That's okay. We can. We have plenty of time on Friday to get through his notes. So for 5, let me just describe. I'm not going to do 6 with you guys because I think you guys get the idea. But what this does, that's going to be flip. Yeah, over x-axis. And that's going to be 5 left. There's no vertical shift. Yeah. There's no vertical stretch.
Wait. I thought you said,
So let me give you one example. Let's look at root x. If I go 5 left, we'll start here, right? And is it going to be like this? Or is it going to be like this? It's like the second one exactly. Because you're going down. So that's just an example of how you would shift it. Or if it was absolute value, it'd be like that, right? Or if it were cube, it'd be like this, because to reflect. Or if it were I'm not about the other ones. So okay. What's this all about? Well, I guess that's if you're trying to do one of the graphs, but let's just move on. Yeah, I think you were supposed to do this if you were to if I gave you guys, we could do this on Friday, where I'll give you a function and have you transform it. We'll say that for Friday. Okay, let's move on to page 3. Okay, in geometry, you guys remember the quilt project, right? You guys did transformations. So you transform figures using translations, reflections, rotations, dilations. So we're going to generalize using proper vocabulary. So what kind of geometric transformation have you made if you replace fx with fx plus k? So we call that a translation. And that's because you're moving up or down. Okay. Here, that's going to be a reflection. Over the x-axis. This is the guys, quiet, please. That's a translation. Nathan, Lincoln can stop talking. Let's move left or right, depending on whether it's positive or negative and what the value of h is. This right here is what we call a dilation. That's where you vertically stretch or compress. Okay, so that's just connecting the geometry to this. But we don't do rotations. Don't worry about that. But we do translations, we do dilations, we do reflections, but we don't do rotations. Rotation is kind of weird. So we don't have to worry about that. Technically, when you flip, you are rotating 180. You want to think of it like that. You could say that, but questions? Okay, cool. Now this right here, it's kind of weird. That's gonna be reflection about the y-axis. And so how will these look? Oh, a reflection. Sorry, vertical stretch or compress.
Wait, are we like studying, was it reflective in the y-axis?
Not yet. Well, actually, it'd be the same thing for the most part.
Yeah.
The basic one, because you're squaring x. So it doesn't matter. But we haven't done any complex ones with that's a pre-calculus type. We're not ready for that yet. So what I'm showing you right now is what happens when you flip about the y-axis. So like, for example, if I do f of negative x, that becomes this. But here, if I do f of negative x, I get that. Well, here I get this. Here I get, which is just back tap to value. And here you get that. So by replacing x with negative x, sometimes it changes. See how that changes? That flips. That flips as well. That doesn't change because absolute value keeps positive, but that flips. So you start seeing these flips. If you put the negative directly to x, sometimes the flip is just like flipping over the x-axis. It could be the same thing. Sometimes it's not, like in case of the middle graph or the second graph. And that's just because square roots and exponents kind of have their own thing going on. So, but that's what to expect for that stuff. So we're going to explore this in more detail tomorrow for sure. Questions? Okay, this is going to be a good one because we're going to now write the equations in the next page. So we're going to get good at predicting the equation from the graph. Okay. So what I want to do, so I'm going to give you guys the parent functions first. And then I'm going to have you guys in your table groups come up with the equations. And I'll come around and help you guys out. So the parent functions here. Let me give you the parent functions for each. 1 over x, x squared, x cubed, 2 to the x, x, x cubed, x squared, x squared, x cubed. What you need to do is figure out a, h, and k. The a values, I think, for the most part, should be pretty easy to figure out. I don't think the a value will change. I think a would be 1 in almost every case. Yeah, I think a is 1, only except for e. E is just a line, so just do point slope form. But except for if it's going down, will be negative. It's like here A will be -1. But all the other ones, A will be 1. So you really actually for I, it's not 1. It's going to be. I think it is. Yeah, no, A is 1 also. Yeah. So what you need to do is figure out H and K. So come up with equations for each of these. I'll do it on the. I'll freeze my screen. I'll do it here, and then I'll share. And I'll walk around in a few minutes to see how you guys are doing. But go in your table groups. Predict the equations for each of these graphs. Yeah, of course. Yeah, totally. Yeah. All of them.
Yeah, I know the fun.
You can get like a magnifying glass to see some of this stuff.
First one, first one, this one, I recommend it. And there's something else, and there's supposed to be like. Perfect that. 5 or 0.5. Is H the X or the Y value?
H is X.
Oh, no, yeah. No, it's going to original equation. I'm sorry.
All right. I got them all. So now I'm gonna see. I got this part. Wait, so we know the general formula is y equals over x, right? So see how what's 2 left. This is so you go up and add what's left. Like here, see how we're 5 down. Now we'll do more complicated.
Do you think that's?
How far is to the left? 1, 2, 3. How far do we have? 1, 2, 3.
I don't know.
Y equals x plus 3 squared. Plus 6. 3 left, 6 down. I know, I'm gonna check it out. Okay. I guess it. Okay, that should be x squared minus.
You can do this on your own. Oh, yeah, I do.
Yeah. Sorry, x minus 5 squared. Well, no, this is x minus 5. We go to 5 down. X squared first, x squared first, then minus 5. You don't need to cut this small. X squared and minus 5 out. But you got the third one, right? That's good.
How is this? This. This, what he's talking about.
You take this one, you can find. That's fine.
No, so this is talking about going down, right?
Yes.
So then why was it?
That's what-
Isn't it minus three? Yeah.
Oh, wait.
No, it's on,
Yeah.
it's on the inside. You're not keeping the whole thing.
Oh, okay, okay.
Yeah, you square the X and then you be a five. A lot of it's order of operations. So you put the -3, no, it's going 3 down. You put the -3 to the outside.
Okay, so it'd be.
Yeah, it's right. That's it.
Whatever I'm supposed to.
I go add just X plus 3 cubed. That's it. Oh, but then also plus, how far is on that? 4. Oh, sorry, that's X, no, it's going to 2 left. X plus 2.
So A is like,
I'm not reading this one.
A is like
plus 2 now.
slow growth.
Yeah.
That's another good pair.
Is that three?
I would, not put the 3 out, sit A is 1. Where's it minus 2?
Oh, yeah.
Yeah, so it's just extra, but then over here, the line, that's good. There's no, that's rust right in here. That's the fair function.
Okay.
It's not, there's no spring at all. Just that.
And the one here's over.
Yeah, exactly.
Okay.
What you're doing is you're causing this X change.
Okay.
Again, we hope out. Evelyn, yes, a question, which one?
Just the first one.
What are X plus?
Right.
Because you can't plug it down with bricks. Oh, get this out. So let's see, where's that? I'll probably go down. That's it, right answer. So I'll probably go down. We passed, right? Yeah. But you do more large. Yeah.
No, I didn't. One over. One over.
You minus. So you still have some few more try. So like, see, this is a combination, we'll actually look at it. I'll probably go left and down. From the parent function, you have vertex. I'll probably go left and down.
C is X minus 3 to the third.
I'll go left.
Cube.
Second.
Why was X minus 3 cubed?
No.
I'd rather.
And he sounds exactly.
I'm ready to do that.
They would name.
Yeah.
I mean,
Oh, yeah, Maddie, big boy.
exactly.
Yeah, I'm going to sit down.
Sometimes the things.
Yeah, no, that makes sense. That's how they did it.
The vertical shift is always going to be considered horizontal power. There is, yeah, so you're going 3 left.
Like 7 minutes starts to get like a little bristles. And my voice changed.
X minus.
And then.
Plus is left.
Yeah, that's why I started to-
And minus is.
And then I was low-key like done with it, like.
Or horizontal,
Yeah.
but for vertical, it's pretty intuitive, yeah. Okay, how are we doing here?
Good on some of them.
Good, that's good. Make sure you put X plus 2 on the bottom. We only went 2 left, that's all.
That's like in the middle of the.
And you don't, there's no plus 1, we're not moving up or down. Right, because the horizontal output still at, y to 0 or the X axis. Okay, there's no 3 here.
Yeah, that's what I was.
Yeah, it's
wondering.
all the A values are 1.
All of the A values are 1? Okay.
I didn't know.
But this one's
It's
negative
like
though.
slow.
That's negative. No, yeah, because you're going up 1 over 1, so that's not much stuff. Keep the cubics. Let's talk about that. So you're going 3 right. You have to do it on the other side. Should be X minus 3. Here, same going 2 left. And 3 up. X plus 2 cube. And plus 3. Guys, the best thing to do is find the center point on the parent function. How does center point move? So 0, 0 is usually the starting point. How does that move? I'm gonna show you guys the answer in just a minute. Oh, hold on, let me answer
I
it.
think that's like, when it's like this part of it, however many that moves, what the inside is like,
Oops, this one.
so it goes. It
So
goes
what-
y
what is
plus
here?
x plus 2
Now
q
here.
plus 3.
How did it
equals
go?
factory.
So how far's the left? Wait. You can't ask her, one here, one. And then you need.
No, like-
Very good. How far to go now?
35.
Good. So you're gonna see x.
Yeah.
Q.
No,
And then minus 2.
right
So
there.
there's not a Q there.
The q,
Because you're causing, what you're doing, you want to move it back left first. Thank you, Val. And focus in. It's an orbital matter. Okay, how is that? Yeah. See that. All right, let's see how you guys do it here. The x squared minus 5 for, good, yeah, x plus 2, that's good. So 10 is the 5 down. So I'll just say x squared minus 5, that one. Let's take a look here. Okay, so here's your concept. So whenever you do a horizontal shift, you take care of that and then you do that. So it moves that cubes. Yeah, because otherwise they might do more vertical shift. Yeah, that's just a one second side of the answer. But still, I'm glad to see these.
And the Jamie locker has like a boxing ring of tape.
Good, yeah, this one is just a. That's a slope of height.
You guys doing haircuts? What? You doing haircuts?
That's why it's in it.
Honestly, I think, no, you can't. If you guys.
No,
do
it's-
haircuts, the school wouldn't let us, but I.
All right, guys, you guys doing great.
We're so obedient. Didn't get haircuts.
All right. All right, okay, guys, quiet down. Nathan. Thanks. Yeah, let's just talk about haircuts later. All right, okay. So, what you want to do is look at key points on the parent function. And how does that key feature or key point change? Hence transformation. For example, look at a parabola. The vertex usually sits at the origin, right? Is it sitting at the origin now? No. Went 5 down. Still put minus 5. Look at this parabola. It's not the origin. It went 3 left, 6 down. X plus 3 squared minus 6. This went 3 right, 6 up, and split. So it's negative x minus 3 squared plus 6. Let's look at the cubics. The center point is usually at the origin. Then went 3 right, x minus 3 cubed. Then went 2 left, 3 up, x plus 2 cubed plus 3. This went 3 left, 2 down, x plus 3 cubed minus 2. That's a linear function, just give me your slope and line intercept, that's easy. This vertical asymptote is usually at the y-axis, it went 2 left. Give me x plus 2 at the bottom. Here, the horizontal asymptote moved -3, make it 3 down. So that's how, and this will take time. It's not going to happen right away, but as we do more and more practice, you start seeing the intuition that goes into this stuff. Okay. And just kind of wrap things up, and we're still going to revisit this on Friday. Can we use transformation right equations for lines? Yes, you can. The answer is yes. What is the equation of a parent graph of a line? Well, y equals x. Duh. What have you learned about transforming parent graphs? Write a general equation for a transform line. You could write like this if you want. Which is really point slope form. So I could say y equals 4/5 x minus 3. And that will still get you the equation of line. So that's point slope form, which I know you guys have seen before. It's really a transformation. That's all it is. Okay, yeah. We just squeeze it all in. It's perfect. Okay, homework. You guys already have. I handed out to you guys. I'll publish to Schoology as well. Work on it. We'll do more of this on Friday. Friday, I'll start telling you more about the tests because we need to start talking about it. And I'll have clarity on the PSAT, what we're going to do about it, because some of you guys will have a conflict. So I'll have clarity on that. Yeah.
I was gone for like 2 days last week, so
Okay.
I wasn't here when I got or turned in homework 12.
Okay.
So it's in its 0. Do you want me to?
Yeah, turn it. Yeah, I just had to do an update. Just turn it. I'll change it. Yeah. Yeah, guys, I did an inventory. I did update your grades. I gave everyone a 5% boost. So everyone's grades have gone up quite a bit, which is good. Let's keep that going. Okay. And we'll have a good week next week too. And you guys, that's mine. Yeah. All right. See you guys. Have a great day. Welcome.